Welcome back, everyone. Let's continue with our program, shall we? So we have Rachit Arora here, who is a consulting member of the technical staff at Oracle Cloud Infrastructure. He's the key designer of many offerings on the cloud for the Hadoop ecosystem as well. So in a world of serverless computing, users tend to be frugal when it comes to expenditure on computing, storage, and other resources that are not actually currently in use. It's a good thing then that Rachid will tell us all about the appropriate storage requirements and options for running Spark on Kubernetes. So Rachid, whenever you're ready, please take it away.
Okay, thank you for the introduction. Hello, everyone. This is Rachit here. And in this session, we are going to discuss on storage requirements for running Spark workloads on Kubernetes. Before we begin, I just want to do a quick introduction as Flora has done a half of it. Like as she mentioned, I'm working for Oracle Cloud in the big data service team, where we are building our own Hadoop distribution and offering it as a service to our consumers. It's called as Oracle distribution for Hadoop. I term myself as more as a general purpose developer, where I basically solve any problem for our customers, and specifically love working on containerization workloads, Kubernetes, and entire big data ecosystem or family of products in big data ecosystem. I used to be a conference traveler, where I used to attend these conferences like this and travel a lot and meet you guys in person. And hopefully next year we can meet in person and enjoy these conferences as we used to do. But today, I hope you will learn from this session, which is around storage requirements for running Spark on Kubernetes. A quick introduction for Apache Spark. So Apache Spark is an open source, scalable, massively parallel in-memory execution engine for your analytical workloads. Think of it as an in-memory layer that sits above multiple data source, where data can be loaded into memory and analyzed in parallel across your cluster. The core of the Apache Spark, it's core libraries. That is the foundation of Spark. That has a lot of libraries for scheduling, doing basic I/O operations, and offers you hundreds of high-level operators that make it easy to build parallel applications. Spark also includes pre-built machine learning algorithms and graph processing algorithms that are specially written to execute things in parallel. It also supports interactive SQL processing queries in real time and also streaming analytics. So you can write your analytical applications in any of your programming languages like Java, Scala, Python, R, right? And you can run Spark on standalone mode, basically on your laptops or on any VM. You can run it in cloud. You can run it on Yarn or Mesos, and even on Kubernetes, right? And data can be accessed from multiple sources like HDFS, Cassandra, HBase, Hive, Object Storage, and many other Hadoop data sources. So since now we know a very high-level introduction of Apache Spark, I just want everybody to be on same page on how a typical big data application life cycle is done, right? So you may be reading data from multiple sources. It could be coming from your laptop, from some TCP port, or from any of your databases, right? So data could be coming from multiple sources, and then there are applications written to ingest that data and either temporarily store it or permanently store in some persistent store, or you do some uh, a- uh, massaging on top of it. So you may have the right data, but it may not be in the right format. Either some null handling would be required, or some transformations like string to int to string would be required. So that's the primarily a role of a data engineer, to make sure that your data is ready for analytics, right? Then comes a role of a data scientist, which uses this data prepared by a data engineer to build analytical models, so that you can get some insights from your data, and then build applications using those models which are trained or deployed by the data scientist, to get value out of it, like building a chatbot, which we usually now interact with multiple delivery applications, which they uses these chatbots, which are built using this kind of a pipeline. And let's, before I go to the main topic, which is like understanding storage requirements of running Spark on Kubernetes, I just want to lay down the picture that why we should be running Spark on Kubernetes, what are the benefits we will get for running Spark on Kubernetes, why we need to consider about those storage requirements. So this role of a data scientist will really help us understand uh, mm, the or acknowledge the value of running Spark on Kubernetes and understanding more. So as a data scientist, I don't want to basically worry about the infrastructure more. I really want to run my analytical jobs. I do want to do like social media analytics to text analytics, run SQL queries, run R scripts, or submit Spark application, or even debug them by analyzing the history server logs. Right? I don't want to wait for the infrastructure to be ready for me and then submit my workloads. Right? And if as a data scientist, if I have to do that on my own, right, how I have been doing in past, and what are the new means I can do it, let's say using the serverless offerings of running Spark, which are available now. Let's say if I have to do that everything on unknown, if I am basically on my on-prem, I would first start with acquiring the right set of hardware, right, which suits those requirements for me. So I may have to get some specialized hardware for running high memory or high IO intensive workloads, and then prepare those hardwares. By preparation, I mean you will be setting up the network, you will be mounting disk, formatting them, installing the prereqs, installing the right versions of prereqs, and then try to install these components like Spark. And many a times you see that these installations will fail, right? It could fail for some missing dependencies, some error in the unmounted disk, some network related errors, and you will fix them and retry these operations, and then after multiple attempts you will have a successful Spark cluster at your disposal, which you can use for running your workloads. And it does not end there. You have to maintain that infrastructure. You need to apply security patches, you need to upgrade to the newer versions of Apache Spark or other binaries which you are using. You need to worry about scaling that cluster based on your increasing analytical workload requirements, and you need to worry about the high availability of the cluster, right? And with the increase in such requirements to create these Spark clusters, you'll think of some virtualization solution which will help you uncover all these issues which you have been facing till now during installation. You'll have some VM images created which will really help you ease on the installation problems, right? So you will just replay those VM images and your cluster will be ready for your usage. But it won't solve your network problems. It won't solve your high availability problems or your patching or scalability related problems. You still need to handle the scale and the high availability of this cluster and make sure that your clusters are uh, always ready for production workload. There is no downtime, and your organization is not impacted, right? So to solve these many of these problems, you will look for managed cloud offerings like Oracle Big Data Service or Amazon EMR or Microsoft HD Insights, right? Which will give you ready-made big data clusters at your disposal, and you need to configure those clusters for your needs and start using them for your running applications. So that will solve your most of your pain points you have been facing till now. And the only thing which could be little bugging you is that if you're not utilizing those compute clusters, like those big clusters you have provisioned 24 by 7, you are paying for those resources if you don't need them, right? So what really you are looking for is a serverless means of submitting your Spark application, where you could just submit your application on demand and don't worry about any of your infrastructure uh, capabilities. And this is where running Spark on Kubernetes really come into picture, where if you have one Kubernetes cluster, you can submit your Spark applications on top of it. That will give you this experience of using serverless analytical workloads on Kubernetes. So what really Kubernetes bring in, like when I said running Spark on Kubernetes, what really it brings in? So Kubernetes is a portable, extensible, open source platform for managing the containerized workloads. It basically facilitates and your container lifecycle management in a declarative, configurable, and automatable way. It has a large, rapidly growing ecosystem behind it. Kubernetes support wide variety of tools which will help you with the adoption of your container journey very easily. It basically takes care of many aspects for you, like high availability. It will make sure their containers, if they're crashing on a particular VM, if it goes bad, it spawns up on another VM. It also provides you easy means of integrating with logging, monitoring, and other security tool. You can use things like Istio to handle all your service mesh requirements, right? So it basically reduces your operational cost a lot. Basically, you can run your analytical and non-analytical workloads on same compute and save a lot on for your compute cost, right? Uh, and when it comes to running Spark on Kubernetes, I have this full blog written why you should consider running Spark on Kubernetes. The basic idea there is that if you're running your other analytical workload, right, your Python notebooks already on Kubernetes, you would also like to run your distributed workload where you are looking for running parallel applications like in Spark. You can choose to run Spark on Kubernetes. It will really help you lower down your resource or optimize your resource usage in a better way, and you could leverage the ecosystem behind it, like logging, monitoring, service mesh in a very effective way. You can go through this blog. which will give you more bullet points if why we should run Spark on Kubernetes. And when it comes to the point that you want to run your workload, Spark workloads on Kubernetes, you are again presented with some options. There is an option to use Spark standalone resource manager itself and run it on Kubernetes, where basically it will give you separate pods for your Spark master, a separate pod for your Spark workers, and based on the number of workers you want, each pod will be mounted on a certain volume, right? Where that volume could be used for your data, your configurations, or you're storing your libraries. And we are going to discuss these storage options in detail. And there will be other pods like Jupyter Enterprise Gateway, which gives you ability to run interactive workloads on this Spark cluster you may have started on Kubernetes. And there will be other pods like History Server pod, which gives you a UI where you can see your past runs of your application and see how was it performing, what was its DAG, how it was doing IO, and how much parallelism you are able to hit, and improve your application performance using History Server. So that is one option. Other option is to use Kubernetes as a Spark resource manager, where when you do a Spark submit application, where you provide hyphen master option, you can give your Kubernetes API server endpoint, and that helps you run little less daemon processes. Like will not be a master process, there will not be a worker daemon. You will be running executor and your driver. So it optimizes in a way that you don't need to have a Spark cluster running. You just run your application using Kubernetes as a master endpoint or a resource manager for Spark. With this option, you get to create your own Docker image, which you can add your own libraries, your application, and use it to submit your workload, right? And there is another option which, in my viewpoint, may not be a very performant option, is to use Yarn on Kubernetes. So Yarn is a production ready or a widely used resource manager for running big data workloads. Is used for many workloads, and Spark basically treats Yarn as a container management system to request and get the resources. And once Spark acquires a container from Yarn, it builds a RPC based communication between the container and to run a driver and executors. So Yarn, if you plan to run on Kubernetes, Yarn will be like a pass through to Kubernetes, where the actual containers will still be coming from Kubernetes, but Yarn is just a pass through in that case. Okay, now let's discuss. We have discussed till now why we should be running our workloads of Spark, like analytical workloads on Kubernetes or in a more of a serverless fashion. What are the benefits? What are the options? Right now, let's discuss what are the different storage requirements we need to consider when it comes to running our Spark workloads on Kubernetes. The first one I would like to talk, so I'm just giving you here a list. We are going to discuss all of the in detail one by one. The first one is like a distributed file system. Not all Spark applications will require you to run have this storage requirement of having a distributed file system. Some of the Spark APIs like model.save or model.load expects it to be running on a distributed file system. So you need a distributed file system which exists on your driver and all your executor pods and accessible from all of them, right? And then you have another type of requirement which is there for typically all the Spark application is local scratch space, which is used for storing your temporary data, uh, which is basically generated in a typical Spark application for every stage to be passed on to the next stage. And this type of storage should be very, very fast, right? So if this is your storage is slow, your Spark application will basically not perform, right? So this should be as fast as possible, and so that your application can be very performant. The other type of persistence you will typically need is for storing your user libraries, especially if you're coming from data science domain where you may want a lot of conda packages or Python libraries to be present for your application. And the size of this user libraries I have seen can grow in GBs and go up to 8 to 10 GBs sometime, if you are relying on your conda packages, right? So you need to have a persistence for managing these libraries, right? And managing the different versions of these libraries also could be a challenge. Other typical requirement of storage is come to storing a metastore. Basically, yeah, when Spark uses metastore to get a view how the data is laid out on either SDFS or on object storage, and it basically get to know about the data, how it is laid out. So you need to have some storage persistence for your metastore, so that it can be persisted for across your Spark application runs. And logs is a very obvious requirement for your persistence, because you want to keep logs of certain runs of your application, so that you can analyze or debug them later. It should not be that case that I have run my application and there are no logs to monitor it. Another typical storage requirement which we have for Apache Spark is for storing history server events. Again, it is very important to persist them across your application runs, so that I can view these history server events across the runs and compare if I need to improve the application performance. So it is very critical to have these events persisted in a way that they are accessible across the runs. And then it comes storing your configuration. So you may not want to submit your confs for each application you are submitting. You may want to create a template which you can reuse across your application runs, so that you don't have to pass it in every run, right? And then you have also requirement of passing your credentials in a secure way to your application, whether if you are trying to access some remote database or some remote system which needs those credentials to be passed to your application. And in the end, it's one basic requirement for your Spark workloads is your persistent data, right? So it could be in SDFS, object storage, and could also be in some block storages. So we'll discuss about that, what are the options of persisting the actual data which I'm using to either build my ingestion application, build my data engineering application, or some building my analytical application using Spark on Kubernetes. Before we discuss the options which are available for those requirements on Kubernetes, I want to discuss about the storage characteristics we have to consider for each of those requirements, right? Uh, First, foremost, the most important characteristics which we need to consider is the size of the volume or the storage we need. So it should not be that I am creating GBs of persistence volume or storage just to store configs, right? So size is very critical. As I mentioned, for certain requirements like scratch disk or temp disk, speed and IO really matter, right? And uh, for certain characteristics, I will need very performant high IOPS storages, and for certain, I may be fine with little cheaper variant, but yes, little less performant also. Then I also need to consider a point whether I need a persistent storage, which is persistent across my application runs, or a transient storage, which basically goes away once my application is complete, right? Especially for enterprise customers or enterprise companies, the safe data erasure is very, very critical. If Because you have to certify with various certifications that you are able to safely delete your data when you are actually want to delete it. So RA minus RF may not do that job when I talk about the safe erasure. So you need to consider the storages which can support your safe erasure for you. Isolation is a very critical characteristics, especially when you are in a multi-role organization where you don't want your data engineer or a data scientist or admin who are in different roles be able to access the same data, right? So there should be means to access control and isolate your data depending on your role. uh, and very key characteristic aspect is pricing, right? So there are multiple options available which it should be able to meet my performance to price when we do that ratio, right? uh, Especially when we talk about the serverless workloads, the provisioning time it takes to provision that storage becomes very critical. If I'm looking, Spark runtimes should come in few seconds. It should not be that case that I am waiting for minutes for my persistence or my storage to be ready, right? So based on your requirement, the provision time it takes to provision that storage becomes very, very critical. And other important characteristics is that this storage should be in a way that it's pluggable. If my requirements are changing without any change in my uh, application or way I'm submitting, I'm able to plug with a new storage and able to scale also if required, right? And the last thing which is very critical to many organizations is that uh, any option I'm considering for selecting the storage, it should be infrastructure agnostic, because there are multiple storage options provided by each cloud vendor. If I'm going, let's say, running my Spark workloads on managed Kubernetes offering provided by multiple cloud vendors, I should not be using storage which is specific to that cloud vendor to avoid the cloud lock-in, right? So keeping all these characteristics in mind, let's see what Kubernetes has to offer to us. So Kubernetes by default provide various storage options in terms of persistent volumes, and the persistent volume claim. So in order to use storage, you need to create a persistent volume. And when you are trying to bind to an application, you create a persistent volume claim. right? And in early days of Kubernetes, it used to add multiple volume types, and this is the list which Kubernetes offered, but they have stopped adding new. Rather, they have given means to extend their API so that you can add your own storage driver and use it in your application. But by default, this is the not a complete list, but the high level list offered by Kubernetes. And as I mentioned, Kubernetes provide you ways to extend or use your own storage drivers, and there are multiple means of writing those drivers. One of them is a flex driver, where vendor drivers should be installed on each node. So basically you are touching the each Kubernetes node in case if you're using flex. But if you use this container storage interface, which is interface you can extend to create your own storage drivers and write and deploy plugins, exposing new storage systems in Kubernetes without ever having to touch the core of the Kubernetes code, right? So these are the options available for you if you want to create your own storage drivers. And with respect to Spark, many a times you don't need to actually mount those physical volumes. You can access these volumes through configuration if the data is either remotely stored or stored somewhere else, like in case of STFS or object storage or even another HBase. So Spark offers you means to configure to work with different storage options. Now let's go point in point to see various storage requirements we discussed, like and we saw some of the options on the Kubernetes side. For each of those requirements, what are the options to consider and which we can use for our application based on our requirement, right? I discussed about the distributed file system, which is not a must-have for many Spark applications, but still, if you need a distributed file system for to be mounted on your driver or onto your each of your executor, you can use network file system and create a PV and PVC. And you have an option of creating a PV at a runtime or even provisioning a network file system on a runtime, which will take, depending on your cloud provider, a few seconds to minutes. But you can also choose to have a big NFS pre-provisioned and create multiple PVs, persistent volumes, and set a quota on each of them and start using PVCs on that. So that option will be very fast with respect to creating your own NFS on demand, right? And then you can also use STFS, where you can configure STFS for your for your DFS requirement, where when you do Spark model.load or persist, it is stored on STFS and not on the NFS. You also have option of using object storage for this particular use case, but I won't recommend that for that, because object storage you will be using for our persistent data, not for storing your models or saving your models immediately, because it may not perform as well as the other options. If you are looking for a way which offer you very good encryption options and safe erasure, Portworx is very one good option, where they provide persistent volumes, or even you can create a separate infrastructure or put Portworx on the same Kubernetes cluster and use these options if you are looking for options which provide you encryption and safe erasure. And for many of the dev scenarios, GlusterFS has helped, but it is little slow in when we But if you want to compromise for your little for your dev, GlissFS can be a very good option. One of the very good option to use for this kind of use case, and even for your persistent data, is to use Alexio, formerly known as Tycoon, which is a like open source data orchestration layer that brings data close to compute for your big data, AI, and ML workloads in cloud. It enables the application to interact with any data from any storage system at a memory equivalent speed, right? So you can certainly plan to use Alexio for solving the for your this requirement. As I mentioned, for your local scratch space or your disk space, it needs to be very, very performant. So SSDs or your SATA are the very good obvious option. One very good option is to use something called in Kubernetes is MTDIR. So the good thing about the MTDIR is that it is tied to the application or your pod lifecycle, and it uses your host local disk space, and this is the one place where you can use for your temp requirements. For logs, you need to think little differently because you don't want to put your logs in your containers and fill up your containers file system, and your container will basically crash. It should be the place where you want to persist log to a remote storage. And the one of the good pattern which I've seen, which working for multiple use cases for pushing logs to remote system, is to use something called as a sidecar pattern, where you run one more container like a Fluentd, which watches from a shared directory or where your logs files are getting generated, and it pushes them on a regular interval to either object storage or your logging service or anywhere, right? So that pattern really helps. You need to be little cautious about your rollovers and gotcha is that do not write your log files in your container file system, right? Basically that will crash your container and it will need to be restarted. Kubernetes will restart and you may go into cycles. So one key requirement, as we discussed earlier, was for user libraries, which was for your Python packages, your R libraries, your jars, or your Conda packages. And again, you have option of using your host path or a shared file system, but they may not be performant for them. This is something that it should be very, very fast. And problem with the host path could be of the security, as if you're not cleaning that up, it may lay there there forever. And even from the security side of it, it's not a recommended way. You can use some of the other patterns like init container pattern in Kubernetes to get your user library from a Docker image and put it into your main container image where you want to use. But one of the very good option which has come up from Kubernetes 1.17 release onward is to share a container file system with your another container in a pod. So you can have your libraries in a Docker image and start two containers in a pod and use this option of sharing the container file system namespace from one container to another. There are multiple use cases for this option apart from using the user libraries. Is for your debugging needs also you can use the same option, but for your user libraries this is a very good option available where you basically share the container file system of another container but use it in your primary application container, but still build your containers separately. So I call this as another design pattern as a composition of containers. If you're interested, you can read more details from the link, and I have another YouTube video talking more detail about it. For your Metastore, where you will be using options like NFS, again, Metastore created out of block storages, or best would be to use external service which give you managed Metastore as a service offering to rely on your Metastore needs. Coming to your configurations, where you want to have configs for your storing, templatizing or reusing from one run to another, is to use something else as a config map, which you can reuse across your Spark applications. Yeah, so handling credentials in Kubernetes is very critical. You need to make sure that you have right RBACs, role-based access roles to your namespaces, and then you create a resource like a Kubernetes secret, which is backed by a vault. So when you create a secret, it is pulling your credentials from a vault and storing it in a secret, but they are access controlled, and use that into your application, which gets mounted to your application and available to your application. Key points here to note is, do not store them in plain text, do not store them in your image. It's a security vulnerability basically in multiple organization security tools will catch it, and you will not be able to use them. Finally, the persistent store option, the most recommended way for when it comes to running Spark on Kubernetes for your storage is to use object storage or a remote SDFS, and use binaries, something which is available in open source called as Strokator, or many other binaries, which help you read data in an optimal way, and even use something like Alexio to improve their performance. But your final persistence is there in object storage. So one gotcha there is, do not mount your object storage as a POSIX file system. That will basically slow your application down, or slow your provisioning time also down, right? So use these binaries to read and write data along with Alexio for your persistent storage. So to summarize this discussion, running analytical workloads like Apache's Spark workloads, Kubernetes present it's some unique challenge, but it solves multiple of your pain points. But these challenges can be addressed by using the right storage option, and many of these options are also evolving as we speak, right? So you can leverage multiple storage options to solve a particular requirement based on the characteristics requirement for your application. So that is basically it, my presentation. I'm happy to take questions now.
Awesome, Rachit. Thank you for your talk. Oh my gosh. Oh, you just froze for a second for me, and it was just like, I'm not going to take these questions. These are too hard. I posted your blog in the chat for people to find on the Why Run Spark on Kubernetes. So people can follow that link when they go to the chat. I saw one question, and I think we might have time for just the one question. I feel like you've answered it in your talk already, but you know, like I don't know.
Sure.
Repetition is key, maybe. When you say Spark on Kubernetes, that mean that cluster manager will be Kubernetes, or can we keep Yarn as the cluster manager and just use Kubernetes containers as cluster infra?
Right. So it really depends on your requirement. Recommendation is to use Kubernetes as a resource manager, as it will save a lot of daemon processes which are not required to be run like a Spark master or a Spark worker. You will just run your driver and executors using Kubernetes resource manager. But if your application is like you are transitioning from, let's say, traditional big data cluster to Kubernetes, you can do it in stages, like use standalone or yarn while you containerize your application workload, and then transition to Kubernetes Resource Manager in different stages. That will help you adopt Kubernetes faster and do it in a stage manner.
Perfect. Thank you so much. Unfortunately, we don't have more time, but
Okay.
I bet that people can find you on the Pine platform. Might they have any more questions? And also, your Twitter handle is now up on the screen for the however many days Twitter will still be around. Thank you so much again for your talk, and thanks everyone for watching.
Thank you. Thank you.
Bye.